All right, finally we get to the thing that I really, really love, which is the dipole, right? So let's say we have our dipole here, M. It's going to put out a field, a magnetic field, that goes like this. Goes along this axis. It has a nice linear field, but as you get away from it, it makes little loops like that, so that perpendicular to the magnetic moment and through the center, what you're going to do is you're going to have the field going the opposite direction as it goes on the other edges. And I guess this comes out like this and this. Right? These are going away, these are coming in, and you have this sort of owl-looking thing. That's your magnetic field. What we're going to care about here, actually, is only this center line. Now we can put together an expression, even an expression for this class, that's good along any position, but that's a little bit ugly, even though it would be something that I could reasonably expect you to know. So we'll avoid that. So that field is, interestingly, let's see, mu naught over 2 pi, I think, yeah. So we've seen this before, but it drops off as magnetic moment m over r cubed, which is the distance along this line, r. So, oops, my cube is in the wrong direction. And I do have something to work. Okay, good. These r's don't really look great. So it drops off as r cubed. So it drops off very rapidly. Now, last time we had, right, this is b over r. So that's going to look sort of like this, right? It goes very quickly. So this is this guy. You'll remember previously we had 1 over r, which looks like this. So this drops off a lot faster, all right? So that's all the r cubed means. And it's proportional to this magnetic moment, okay? And if you wanted to do this for a current loop, all you have to do is remember that your basic current magnetic moment is IA, the area of the loop times your current, and you can find out what's going on along this center line. Okay? You can compare this to what happened in the previous thing in the center, and we'll talk a little bit about that. So that's pretty reasonable. Actually, I'll talk a little bit about that in a second, just for fun. But right now we just want to say that 3, the field from what we call a point dipole or a physical dipole, decreases as the cube of the distance from the dipole. Okay. Now we want to talk a little bit about this. So what happens there? Well, we just talked about, if we had this circular arc right here, we would have what? The field at this spot right here has to be mu naught over 2 I over r. Do you remember that one? Hopefully you do. But why is that a little bit different from what we've been doing previously? Well, that's a little bit different than this, because this at this spot is infinity, right? This is infinity. This guy I just said here It has a finite value, right? So we'll call that BC, right? So that has a finite value there. That would tell you that for this real dipole, it should have a dependence sort of like this at the far end, but somewhere it's going to diverge, sort of have a flat region, and that comes down like that, okay? And that's going to be a big part of what we talk about later on in the example. So in the example, I'm going to take this, and I'm going to combine it with another equation, which is B sub r, where r is the radius of this current loop, is going to be equal to mu naught m over 2 pi r squared, where this is r, plus, we'll call that z squared to the 3 halves. Okay, so that's what the example is going to be. Is we're going to look at this guy here, with this guy being r, and this distance up here being z, and we'll look at what the field is at a point there, like that. And maybe make a little more detailed graph like that. So I'll have the ability to add graphics for that. I will add graphics to that. I bet I could figure out ways to add graphics to this, but let's just not go there. Let's actually finish with these things. And I'll make one of those things, and we'll end up with an idea about what's actually happening in that situation. So, right, this thing, I guess you'll notice if z is 0, if you're right here, is going to be very similar to this guy, because it's going to be a constant thing, mu naught m over 2 pi times r squared to the 3 halves, which is r cubed, right? But we don't have here the mu naught, so this is mu naught a, or this is IA here, so this guy, so that's a pi, and that's going to cancel out, and then we've got the mu naught. This is also going to have an r squared, so this is going to leave only one r there, so that's fine. And then in this case, this actually, get rid of that, you have z squared to the 3 halves. That matches this one exactly. So this gets both of these limits, and it's also going to let us talk about what happens near this. So this guy's called a physical dipole, right? And it's called a physical dipole because it's generated by something like this. This guy, of course, was called an ideal dipole, or a pure dipole, or a something else. Ideal, I had another name for it. A point dipole is what I called it. So if this was just a point, you end up with something like this. This is sort of what you get from an electron, and then you get a different expression. You get infinity right at the electron, which is always a problem with electrons because they're such small particles. So we don't like to play with electrons for these examples. So what does that mean? That means it's time to go back to lesson 10 because I forgot to record it. All right, so I'll record that before I edit all of these things, so you won't even notice. All right, after this we'll do lesson 12, which will be a bunch of different applications for magnetic fields, magnetostatic fields combined with electrostatic fields. And after that, we'll be done with magnetism, and we'll go on to electromagnetism. We'll talk about the interaction between those electric and magnetic fields and what sort of interesting things happen there. And after that will be optics. All right? Bye now.